It's only gonna happen once a week, like for your class.
Yes, you only get my, well, oh, and that, by the way, it only happens once a week. Here's the deal. If you need help, just text me and I'll set up a Zoom meeting right then and there. Like, if I can, I mean, so you guys, this is the official class meeting. If you want to talk with me, I would be more than happy to do so anytime, as long as I'm available. The only other thing I have going on, because I can't see my grandson, is I'm down at the mathnasium thing, helping that guy out. He has a remote thing going, so I go down there every once in a while to help him. So if I'm look, I got nothing. I'm sitting alone in my apartment with the sloth and the squid. So please.
Why can't you go see your grandson?
Because my son, rightfully so, is worried about his health. He doesn't want me bringing this to the virus over. So yeah, I'm sad. But what are you gonna do?
That's your blood right there, running through that boy's veins.
Well, yeah, but yeah, but I don't want to add virus to that too. So let me get my better shape. Because my son. Let's try that. Yeah, but I don't add virus to that. Better. Why do I hear myself? All right. Okay, here we go. So, do you guys have?
Let's pull that paper.
Yeah, this guy. I mean, well, whatever you're going to take notes on, because I got to go over a couple things before I can assign anything. We have some important stuff to do here. See if you got that, or just get out something to take notes with.
How's Danny doing? Good. Well, tell him we miss him. It's hard not seeing them.
And by the way, if you'd like, you can always,
yeah,
you know,
well,
I live by myself, so unless the sloth starts talking or something, but if something's going on and you wanna mute yourself, feel free, and just unmute yourself when you go to.
Oh, good. Yeah, and he's been doing great. Like,
try this. All right, so I have that, and I have the ability to jump to. Let's see if I can do it real quick.
okay.
All right, there we go. So I can go back and forth between me and whatever I'm writing. Look at that. All right.
Yeah, that should be great then.
There we go.
I'm
All right. How's that look for you guys?
I am sending out
Fine.
Good?
I can see it.
You can see it? See it all right? All right. Well,
Wait,
I'm looking
wait.
present.
Put
Let's
you on
go
the main
to,
screen.
Double tap the screen.
Okay,
yeah, if you double tap mine, you should be able to see.
got it.
So let's go
Wait,
down
where are we at?
Mine too.
here. So the one that has the different processes. We're going to talk about the different processes.
What's a Khan Academy video?
Well, yeah, there should be one on it because it's like one of the most important things. By the way, I think most of my teaching is not going to be done this way. This just seems to me to be really annoying. If I was you, I'd be really annoyed right now.
Yeah.
I'm not going to lie. I mean, I would. It'd just be like, God damn, can we get this started? So it'll be a lot more of this is going to be via like a screencasting kind of thing. And then we'll save more for questions when we're together. Let me focus. There we go. Okay, so isothermal process. We have 4 processes we got to go through real quick. Process number 1, isothermal processes.
Oh, ISO. Where's the ISO at? What?
Yeah.
In the paper.
There's
We wanna,
we did this just before we left. There should be a bottom right-hand corner of one of these pages. There's like, it really doesn't matter if you just want to write down on a note piece of paper
right, the learning.
what an
still has to
isothermal
be-
process is.
I can't find it.
Right.
It's on the page. It has the heat transfer thing.
Can't find it.
Just write it down on a piece of paper then.
I don't want to write on this paper. I have this big paper.
You are. Well, you haven't changed, have you?
You gotta write it.
I see heat transfer.
You got heat transfer.
Yeah, I see heat transfer.
All right, in the bottom right-hand corner of that paper. Let me get
Well, tell them this. Tell
There
them
were
that when we
there
come
were
back-
4 smaller papers because I had to make things complicated that we cut out.
Yeah.
All right, so the one if you haven't glued those in, it says
Yeah.
processes where heat is not added or removed.
Yeah.
All right, and then we stuck 3 papers on top of that.
Yes.
We're on the top paper.
Mine doesn't say ISO. I must
No.
be missing one.
All right, well, that's you wrote that, not me. I that was blank. We wrote it.
Oh,
That's part of the notes.
I wonder I couldn't find it. Okay. I couldn't. See, this no school thing is not working already.
You know what? It's new for all of us. Be patient. So yes, this is the first processes where the temperature remains constant.
Yeah, and that's,
All right. So some things you need to the standard thing that you're gonna see is basically some sort of container with a movable piston.
And a weight on top.
And well, it depends on the situation
that's fine.
and the gas inside. So
Right.
sometimes they'll have a weight on top, sometimes they won't. Sometimes they'll lock this into position so it's not movable. Depends on the situation. In this case,
Well, what's your email?
here's what you need to know, and that is generally the process will happen slowly.
That's fine also.
So if this changes volume or whatever, it will happen slowly. Oh, I hear
What will
myself.
happen
So that
Okay.
the temperature remains constant.
Wait, what's happening slowly?
So for example, if I compress this, right,
Uh-huh.
the temperature should go up.
Yeah.
But if I do it slowly, there's time for the thermal energy to leave the system.
How would it leave if it's
Yeah.
So like if you put a hot glass of water out, it's going to cool down, right?
so
So it's just a matter of if it's assuming it's at room temperature, if you compress it, it will go higher than that, and that heat would eventually leave.
Remotely, because, you know,
So
some kids have more
If you
support.
lower it, so if you do that slowly, or you wait a while after you do it, then the temperature will not have, from before and after, will not have
That
changed.
we will be just reviewing, but I'll get that email sent out and you just reach
Cool.
out if you have questions and please tell Danny I said hello.
So for
temperature
example,
remains 0.
I'm sorry?
yeah, delta T, change in
Oh,
temperature.
okay.
Oh, that's okay, Miss King, like a king and
So
queen.
here's the interesting one,
Mhm.
is you can
Right.
add heat to this and still not change the temperature.
I'm the one at Forest Oak, yeah. Yep. He's
Because
with me
it's
most of the
possible
day.
to add heat, so put flames underneath of it,
All
and
right, well, take
instead
care
of the temperature rising, the piston would rise.
Have it.
And it is possible to add heat to something and, believe it or not have it not change temperature if you allow it to expand, for example. So let's do this. Let's go back up here for a second. Have we talked about the first law of thermodynamics?
No.
No.
You have nothing there?
Nope.
Oh, well, shit, we should try to do that first then. All right, you ready? So-
No, no.
No, I'm gonna wait.
Writing defense.
Can I see the isothermal process again so I can screenshot it?
Yeah, there you go. By the way, I'm recording all these as well, and I'll find a way to post them on Schoology. So if you miss a class,
Okay, because I'll put it in my notes later.
okay. It's just too early to write.
Way too early.
Okay, now are we moving or are we going?
We're gonna jump up for a second because I forgot. I guess we hadn't covered the first law of thermodynamics. This is the most important equation that we have. Cool. All right. So change in internal energy. U is internal energy.
He went on a whole thing about how he's trying to get his kids to learn to tie his shoes all his home.
Internal energy is U. When you see that, when I see that, I tend to think temperature. In fact, here, let me write this down. So you got, I'll come back to that actually. So equals. All right. So there's two ways you can put energy in or take energy out of a gas in one of these like container thingies. One way is to add or subtract heat. So in other words, put it under a flame or put it in a bucket of ice. So that would be Q. Heat added or removed.
Oh, okay.
Wait, so Q stands for
Yeah.
temperature?
No. It stands for an amount of joules of heat, of thermal energy that is transferred to or from the gas.
Oh my God.
So it's basically, it's not temperature. It's the energy you put in or after. Temperature, ready, is, here's where temperature shows up, or right here. So you know how we have PV equals nRT, right? Why can't you see that? There it is. You know how you have PV equals nRT?
Yes.
Yes?
Yeah.
Both of those are internal energy. There's just two different ways of looking at internal energy. I tend to look at it more on the temperature side. Generally, I think it helps when I do that. So a change in internal energy is really a change in, probably a change in temperature, or it could be, but then if PV changes, temperature has to change. So, but yes, this is the best way to look at internal energy. Cool? That's different than the heat you would add that would change the temperature and possibly change the internal energy. Yeah?
Yeah.
Okay, so this right here is really changing that, is what we're talking about here.
Oh, so you could rewrite it to like
You could.
whatever's on that side of the
Yes, yeah, and you could you could probably even do PV over there because they are equal. Yes, that is, you got to remember that this really links to the ideal gas law. Probably links to that. This is basically going to have to be given to you, or you're going to have to calculate it. There's no separate equation for it. They're either going to, put it in a flame and say it absorbs this much heat energy in joules, or they put it in ice and the ice absorbs this many joules. That's really what that is. Now, the next part. There's another way to put energy into or out of this gas. And that would involve either smashing this lid down or having the gas push it up. In other words, this movable piston is the other way to change the energy. Think of it this way. If the gas raises the lid, is that energy out or energy into the gas? So if you had to lift something heavy, is that energy out or in for you?
In.
You get energy from lifting a box?
No,
You're putting energy in.
To the box, but I'm saying for you. So you're the gas.
Oh,
is that energy out or in for you when you do work? Out for you, right? So that it's all about the perspective. That's why this makes this tough. So It's the work, it's plus or minus, I always put plus or minus, the work done by the gas. No, shh, don't write that down. See, okay, in our case, on the gas.
But you're not doing it on gas. If the gas lifts it up.
Okay, right. So I would, ready? If the gas lifts it up, even though, you know, weight or whatever, I'm pushing down on this, then the gas, then I did negative work, didn't I?
Who's
I was,
you, the gas?
see now, so here's the issue. Ready? Some textbooks and folks look at work as work done by the gas.
Yeah.
Others, like AP, look at it as work done on the gas.
So the piston would do work on the gas.
So for us, and so in our equation, technically, this would be a plus sign. Because positive work on the gas would be energy in. That would be me pushing this thing down. I do positive work, that's energy in.
Yeah.
If the lid goes up, I had work done against me, but see, I like to look at it as it's just energy out, so that was going to be negative. So whether this is positive or negative comes from which way this thing's moving. The best way I like to look at it is that energy in or out. You can usually figure that out by looking at the situation. In order to raise its lid, the gas, that's energy out of the system, right? The gas has to give up some energy. In order to when the lid gets crushed down on it, you do work on the gas. You give the gas energy. And in fact, has anybody used a bicycle pump?
Yeah.
Right? So when you do the bicycle pump, the cylinder gets hot. Try it sometime. So when you do a manual bicycle pump, the cylinder, it will get hot because you are putting energy in, and the gas, every time you compress it, rises in temperature. And so there's an example of you do work when that ends up as being internal energy into the gas. The textbook that we use, mother effers, look at it from the perspective of the gas, which is a pain in the ass. They make this on there, for them, this will be a negative. I like this way better because for me, I look at it as positive is energy in and negative is energy out, and it's easier that way. If you do this as a negative, then you get situations with a double negative, and it's just a pain in the ass. So that will be the hardest thing. Here's the other thing: if you're doing this and your answer is wrong, it's probably because the sign on this is misinterpreted. It's probably this should be negative when it was actually positive, or vice versa. But this guy is the most important equation other than the ideal gas law. It's really just this, the ideal gas law, and a little bit of that average kinetic energy is, what is it, 3/2 Boltzmann's constant times the temperature. Those are really the only three. So, okay, so you have this. Cool. So if isothermal processes, ready? This is important. If the temperature doesn't change, which one of these doesn't change?
The work. Right?
Mm-hmm. Which one of these is temperature the indicator of? Because work is like
Q.
constant. Q is the energy in or out, but the internal energy.
Oh.
Oh, yeah.
Right? So if the temperature doesn't change, does internal energy change?
Mm-mm.
The answer is no. So one of the things you want to write here.
So that means no work is done.
Yeah, you can do work. See, the thing can do work as long as heat comes in or out of the system.
Oh.
Yeah, see, so you got three things that can change. You're probably going to keep one of them constant, and the other two are going to change. Your job is to figure out which one's constant. In this case, it's the change in internal energy is 0. All right, for an isothermal process, where you don't change temperature, then the internal energy can't change. So if you push down on this, which is energy in, it has to leave as heat out. It can't, the gas will not, can't increase temperature. Now it might, and for a little bit, but eventually that heat, so those problems will be, isothermal will be, it's compressed slowly, or it's compressed and then a long time after that, something like that. So it's the beginning and ending situations have the same temperature. It might have gone up in between, but then that excess heat comes out. So another way to look at this is Q, and I'm just going to absolute value, and work have to be equal to each other then, don't they?
What do you mean equal?
Well, if this is 0, right?
Yeah.
Whatever I put in here, this
Yeah.
better be the same number, but the opposite.
Inverse.
Right,
Yeah.
and so that's why I just use absolute value. If I wrote, I guess I could write Q equals the opposite of work, or vice versa. Work is the opposite of Q, doesn't matter. But they're going to be the same number.
Yeah.
So the trick here is you see isothermal, knowing what to do with this, and how, so that you can solve the problem, kind of thing. Cool?
Mm-hmm.
All right, so let's look at another one. Processes where the pressure remains constant. They're probably not going to use this word but isobaric. Like a barometer, measures pressure. So isobaric, constant pressure. All right. So they are the ones that the quickest way to spot those is a movable piston with some amount of weight, noticeable weight put. They could just be the weight of the piston too. But what happens here is that the area of our disc doesn't change, and the force downward doesn't change because it's the same weight. So no matter where this is, and it still is applying the gas has to be at the same pressure, because it will move this thing until it is the same pressure. So this is the way you want to keep in mind, is this situation here is a good indicator that you are at constant pressure. Now, constant pressure is interesting because the volume can change. So I don't think there's anything in here that we can actually rule out. So constant pressure may be some of the trickier ones. I think the entire first law would stay in play, because we can't rule out work, because here's what you want to keep in mind. Work is whenever this moves.
Mm-hmm.
All right, because it's force times distance, and if this doesn't move, and no work getting done. In a problem, you might recognize Q by heating it or cooling it. If they don't do that, maybe then you can, maybe they tell you there's no heat in or out, then you might be able to rule out that. But in this case, this knowledge does not really help us. But I will tell you this: in this case, be on the lookout. A free body diagram might help. In general, if this thing's free, because it's going to go until it's balanced. So a free body diagram in this case might be something that helps. But in general, all of the first law of thermo is in play. All right, let's go on. Next one. If we keep volume constant, I think it's isochoric. I think I spelled it right. It's called isochoric. I believe that's a CH. The word is not really that important. The problem is probably not going to say a gas is heated isochorically, and you're like, what the hell? It's going to say, a gas in a fixed size container, or a gas where the lid has been latched down, like can't be moved. Something like that. So what does this tell us? If what's definitely not changing that? If the change in volume is 0, that means this thing isn't moving. And if that isn't moving, which of these terms has to be 0?
Work.
Work.
Bingo. Work is force times distance. If there ain't no distance, there ain't doing work. So the work in that equation has to be 0. So you really have change in internal energy is equal to the heat added or removed. If you think about it, it makes sense. There's only 2 ways that you're going to raise, that the temperature is going to change on this thing. You can either add heat to it or take it away, or you can do work on it. Well, if you can't do work, it's got to be heat interact. So this, if you know something happens at constant volume, you can rule out work. So these are the little things that you want to, quote, study. You want to, is what each of these tells you about this equation. All right. Pretty much straightforward there. All right, last one. So any process where heat is not added or removed, in other words, Q is equal to 0 joules. Now I think the spelling on this is going to be right. We'll try it. Is an adiabatic process. They will use this word and expect you to know what it means. And it's fun to say, adiabatic.
So that means change in U equals work.
All right, so we would come down to, if it's done adiabatically, then what that means is your change in internal energy would only be done by work on or by the gas. So these tend to be processes. Here's how you recognize them in a problem. So remember back here, if it's isothermically, they tend to be slow processes, right? Adiabatic processes tend to be fast or quick processes, because let's face it, can you really keep the heat? If something is hot, like hot chocolate, can you really keep heat from leaving it?
No.
Even with a thermos, you give it enough time, it's going to be gone, right?
Yeah.
So this really only is an approximation that happens if a process happens really quickly, like compressing the bicycle pump. The heat doesn't have time to necessarily leave the bicycle pump, and so the temperature of the gas increases. But since you can feel it being warm, there is eventually heat leaving the thing. So, but the first law just becomes this right here. All right. Adiabatic, Q is 0. Isothermal, delta U is 0.
Mhm.
Isobaric, all bets are off, everything's good, everything's in play. So they may be some of the harder ones. Isochoric, no work. There's no change in volume, no work done. So those are the connections you want to make when you're looking at things and solving problems. All right. Now, the other big thing that we need to make sure you guys understand are PV diagrams. They're massively important. If you've looked at any of the problems, there's probably a ton of them in there, I think. I mean, yeah, there's one on the first page right here of that one. That's P and X close. Yeah, standard problem there with a PV diagram. So yeah, they're going to be all over the place. Here's a PV. Yeah. All right. So we need to look at those processes. Okay, so let's do that. You good? You ready to roll? Here we go. This is important, but when we're done this, I will do all of this garbage as a screencast. And I'll probably also do a screencast for this, And if you're going to read about anything, how to handle PV diagrams would be a really, really good one. And connecting these, the diagrams I'm going to draw, to these processes. All right. First thing you want to keep in mind in a PV diagram. So it's pressure versus volume. And so PV equals nRT, right? There we go. So the more internal energy is the bigger P times V, right? So where are bigger P times V's located? Well, there where you have big volumes and big pressure, right? So out this way, as you move this way on that graph, your internal energy increases. So higher internal energy. They'll ask you, there are questions like this. They'll basically give you like 4 points and say which one has if they have the same amount of gas. So you have 4 substances at the same amount of gas in these locations, which one has the highest temperature? That's a standard question that you're going to see. Or they'll say the same gas is taken from here to here to here to here. Where is it going to have the highest energy? The highest internal energy? Whichever one is the most that way. All right, up and to the right. That's really all there is to that, but it's that important. Like higher internal energies are up here, lower ones are towards the origin this way. So it's, what would a constant internal energy look like? Well, let's take a look.
Would it be a straight line?
Horizontal. If this is constant, if the internal energy is constant, temperature is always the same, right?
Mm-hmm.
So let me just see if this is work done on the gas, work done by the gas. All right, so I'm gonna do some of this here, I think. So let's look at isothermal. So if you have an isothermal process, in other words, the temperature stays the same. There is no change in internal energy. So if P is your Y and V is your X, you would rewrite this as P equals nRT over V. But this is a constant, right? For an isothermal process, this has to be constant. So this is really Y equals some number over X. What do those graphs look like? Now they're 1/overs. So their inverse graphs are going to look like this. They're going to be asymptotic to both axes like that. Cool? Yeah, anybody awake?
Yeah.
I still am. All right, so this graph, this curve, is called an isotherm. I'm not sure I graphed it perfectly right, but you get the idea. Now,
But so does that mean that the internal energy is like lower than just
the internal energy, interestingly enough, the internal energy at every point in this line is the same.
But it's still like low versus like something.
No, you're right. It is the same. So for example, you're right. It is low. If I had, here, hold on, red. I got quite the setup here. So this isotherm right here, right, is all of these points are at the same internal energy, but the internal energy here is more, the temperature would be more than here.
Mm-hmm.
All right, because the farther we go that way, so there are an infinite number of isotherms, places where the temperature is exactly, 72.1 degrees or something like that, but, and all these would have the same temperature, but their temperature would be higher than this one. Cool?
Mm-hmm.
All right. So what's next? Let's go. Isobaric. So constant pressure.
Oh,
Well,
so that means it's 0, right?
well, the change in pressure is 0, but the pressure is always the same. So these are horizontal lines. If a gas goes from A to B, from these two states, and it has to be a constant pressure, then the pressure will never change. It has to be a horizontal line. But it went from which point has the higher internal energy?
B.
Right. B is so energy was put into the gas, was it not?
Mm-hmm.
Now, what we don't know is how. It could have been put on a stove. It could have been put on a burner and had it heat added, or it could have had work done on the gas. Someone could have compressed it. Let me make sure that's right. Pressure is the same. Internal energy went up. Yeah. So, but actually, probably would have been a little bit of, let's see, pressure, temperature. Yeah. So you could have compressed it as well, because expanded it, right? Because the volume would go up. Yes.
But
From here
if
to
you
here is an increase in
expand it,
volume. All right. So you increase the volume.
then you
Ready?
also have to increase the temperature, right?
Right. You have to. And here's what I know. If you increase the volume, but you maintain the same pressure, think about it. If you expand the container, shouldn't the pressure go down inside?
Yeah. So you have to.
All right. So
speed it up.
what do you have to do? What's the only other way to put energy in?
Speed it up, add heat.
You got to add heat to it. So look
Q.
at going from A to B. I know that volume expanded.
Wait, but isn't the volume expanding work because it's the piston?
Right. It's so the gas put energy out by lifting the volume, right?
Yeah.
Lifting the lid. But when it was done, still had more energy, didn't it? So in that case, it actually, the work done would be, this would be negative.
And that would be positive.
This would be a positive increase. So Q has to be a lot. There's a lot of heat added, isn't there? Because not only did you,
zero,
wouldn't what be 0?
the change in U.
No, this would definitely be a change in U. The internal energy here to here is definitely different. The only time it's not is if you're on one of these adiabatic, one of these isotherms. So this is definitely an increase in internal energy. So this managed to be positive. We know this would have been negative because the volume increased.
Yeah.
So Q must be positive and pretty darn big, right? Enough to cancel this negative and increase this.
Okay. Makes sense.
So like I look at that, it's got to be heat in, because the volume increasing means the gas had to expend energy to lift the lid. So I must have put more energy in to get it to increase. So let's look at, by the way, is there work done? Is there some work done, either positive or negative?
Yes.
Yes. Is there work, if something went from A to B here, would work be done?
Well, you said they're all the same pressure.
Right. Does volume change?
You know that the change in the heat would have to cancel out then.
Oh yeah, I'm not, yeah, all I'm asking is there work done?
Yeah.
And there has to be, because volume changes, right? From here to here, we moved left to right. If I went from here to here, I'd go right to left. Either way, the volume changes. So if there is a change in volume, you've got to remember there's work being done, positive or negative. Now, isochoric. Volume stays the same. So I might go from A to B, say like that. But it's going to be a vertical line because volume's not going to change. Is work done here?
No.
No. Isochoric, there's no, volume doesn't change, there's no work done. So this decrease in internal energy, do you agree with me on decrease? Right? If up this way but this is definitely closer to the origin.
Yes.
Must have come from cooling the gas. It's the only way.
Oh, there was no work done and heat was taken out.
So heat has to be added, and if the internal energy drops, it's got to be heat out.
Yeah.
All right. So we have, so isochoric Constant volume ones are vertical lines. And things could go from A to B. Like they could go, the direction is depending on the question. Now, I don't know why I don't have another one here. So we're just going to have to do one somewhere else. That's all right. We'll do one right here. So somewhere else on your papers, flip it over or something. Pressure, volume. So adiabatic, if you're not told that it's adiabatic, you're going to have a really hard time determining if it's by the shape of it what it is. Because what an adiabat, that's the word we call it, by the way, an adiabat, which is cool. It sounds like some sort of weird animal. So the best way to look at it is this. Let's say this. So let's say this is one isotherm, and this is another isotherm. So two different internal energies. An adiabat is a curve that connects two of them. Looks something like that. You're not going to tell from its shape what the hell it is. And they'll have to tell you that it's an adiabat. It's not a big deal. But this is what an adiabat is. So it's another curved one like this. It has a similar shape, but not quite. It's helpful to remember that an adiabat from point A to B will connect two isotherms. I'm not sure that's helpful necessarily, but work is done as well because there's a change in volume. And there has to be work done because we're not allowing heat to escape or be put in. All right, so this is the best way to look at adiabats. All right. So what do I want you to do? Let's take a look at this folder, shall we? All right, can you see my screen now?
Yeah.
All right, good. At least somebody responded. Somebody's awake. So you have, this is really weird because I really don't even look at you guys. So it's like I'm talking to like my apartment. All right. I believe these are the two that I've given you so far. The yellow and the pink one.
I have the pink one.
What?
I don't have a pink one.
I may have given it to you when it wasn't pink.
No, I've never. You took mine back.
Bruh.
Well, then go into the freaking thing and get it.
Can you just give me one? I don't want to. I can't print all that out. Please, I can't print all that.
You want me to risk my life by going out into the real world and bringing you one of these?
Yeah, it's building your immune system.
You know I will, so shut up. But yeah, this is it. All right, I'll get you a copy. Does anybody else need a copy?
Wait, let me make sure. Let me look them up.
That would be nice because I gave them out before I made them pink. I thought I gave them, I don't know, but
I have the first one, and that's it. I just have multiple choice one.
all right.
I can't even see because of my freaking background. So.
I can't promise, by the way, that everything here I'm going to be able to bring to you, but
No, just the multiple choice too.
all right, because here's the other stuff that's in here. All right, I would want you to do this. We'll try to do it this way. I want these two practice multiple choice first. Look at a bunch of those. If you get questions, I'll put a screencast about entropy and heat engines and all that. And then I really want you, I think, to work on these next. And you could, if you don't have a copy, you can always just write down your, and it's not that hard to write down your answers on a piece of paper. Yeah, I would look at these next because they're gonna. So, for example, here's this one. Rank the temperatures of the gas.
So whatever has the highest internal energy.
And which is going to be the one that's up and to the right. I don't even need to do calculations. So this is gas going from different states through two constant pressures and two constant volumes. We'll have to look at work in that case. Well, temperature. So you should know this, the area under this is the work done either by or on the gas. So the area between under here, in this case, would be done by the gas because it's going from left to right. So this would be, yeah. So this is going to be negative work for us if you calculate the area under there. So that's why they change in temperature, not a big deal. Let's see if they talk about work done. So here you go, work done by the gas. Right here, this one, there is no work being done by the gas, right? Because it's vertical. There's no change in volume. There's no work being done. So it's really whatever one of these has the biggest area under the curve. All right. So let's look at these. I've also included here, since I'm not around all the, to just pop in. I've also included these, bunch of the readings from the thermodynamics chapter for our textbook. Just be aware that their interpretation of work done is the opposite sign from the way we would do it. So if they're doing a sample problem and you're like, why is work negative? And you would think it would be positive. It's because we're doing a different way of looking at it. AP looks at it the other way. But yeah, each of these is just the section. Here's the one on entropy. All right, they're not too long. I recommend reading them. The student study guide isn't a bad deal. I've included that too. It just gives you the important terms, the equations, some summaries of the different sections. So that's quick. If you want to read just one thing real quick, that's not a bad one to do. I put in the problems and the concept questions from them. We might look at some of those, but they're like the ones I'd give on WebAssign or something if I was doing that. So I'm probably not going to. We're going to focus on free response. So the last thing we're going to do are these thermo free responses. So once we feel like we got these taken care of and I got another set of multiple choice and these, we'll do the free responses and go from there. All right. So do the abridged typers one. That's the name of the book they come from. Don't do the full thing. Just do this one. So I would focus on this and finishing up these two and watching whatever notes I give you on the bottom part of this. And I'll include anything else that I think I might have forgotten earlier on. So yeah, I'll just do a catch-all with the notes and we'll hopefully wrap that up. Cool?
Yeah.
All right. I'm going to try to sneak into the building today. They are hold on. I'm just making sure. I think. Okay, so I'm learning. I missed. Ariana showed up to the meeting, and then I didn't put her in the room with Bert. She just sat there alone. So, poor thing. All right, so I think we're good. Let's feel free to watch a little Khan Academy as well, including anything that didn't make sense here should make sense there. Hopefully, I will post the notes later on today for the rest of this. Cool?
Yeah.
All right. Friday, or anytime you really need it, but Friday definitely 9 in the morning. You can come and get help.
Okay.
All right. I'm going to. You guys can go ahead and log out. I'm going to go over to the other meeting and see how they're doing.
Okay.
All right. See you guys.
See ya.
Thanks for waking up early.